I'm Sandra Gordon. I'm a staff scientist within the Benneberg Group. We have actually a number of different research projects within the group, and we're part of a larger research group called the PTH Group. This is all funded through DanStem at the University of Copenhagen. So my work is mostly in regards to, in a way, personalized medicine by taking AML samples, so acute myeloid leukemia, and testing this on a panel of currently available or, let's say, off-license or off-label drugs that you can use for AML. So we're trying to see if we can measure a difference. So do these drugs have any response in the patient material? The idea being, of course, that we know any drug has a group of people who respond and a group of people who don't. But we don't have very good ways of determining, are you a responder or are you not? So this is kind of like the first step in setting up something where you can help determine and direct drug selection for treatment. To kind of say, okay, we maybe have many of the drugs that we need, we just don't have the best way to select which drugs go to which patients to get the best outcomes. Obviously, some of the patient samples that do come to us essentially are drug resistant. If you have a relapsed patient, that usually means that they are now resistant to one or more of the cocktail of drugs that they get from their initial treatment. So now we have something that we know for sure for 2 or 3 things. It doesn't care that you've given those drugs. So that's also, I think that's, especially when you look at our choice of work, is aiming a lot more towards those relapsed patients. Because as I understand it, quite often the very primary sort of treatment for AML does work. But it will come back, and then where do you go? Because now it clearly is resistant to something within that cocktail of drugs that you give initially. So now what's your next move? And at some point, you know, it outmaneuvers you. And it's also, yeah, where to go. It's a multiclonal disease. So now you've gotten rid of the most popular clone. Now the genetics of the new one is slightly different than the old one. Okay, now pick something else. Yeah, I mean, understanding clonality it's a big aspect of leukemia, as it's not so well understood in normal hemopoietic systems. So like how, when you have a stem cell, how many times can that divide before it dies? Does it die? Do you have a set number that you get in your life and then that's it? Does it make more? I mean, there's a lot part of that in regards to just the basic science that we don't understand, no matter if you're healthy or not. So then when you sort of say, okay, now you have a disease and we don't know, like, will that clone that creates that disease burn itself out? We don't know, because we don't know if the clone that creates the normal cells burns itself out either. So it's, there's a lot of basic research that is, that still needs to fill some holes in our understanding. And so there's tons of work to be done. AML is very hard. It's extremely diverse. And I think that's actually one of the biggest, or one of the hardest things about it, is that I had previously worked with CML, so chronic myeloid leukemia. And this is, for the most part, one genetic change. Every patient has the same genetic change. That's what's created the CML. AML, every patient is completely different than the next one. So there are some broad groupings, but the genetic change that actually created the disease is, it could be one of like 500 different things. So it's, in that way, it's not really one disease, it's a lot of different diseases. So everything we can do to kind of like piece that apart, to say like, okay, you have AML, but you have this type can help make better drugs down the line for, if you work more drug development, then you can start to say, okay, we can start picking apart at specific genetic mutations that might be useful, but also just like of the drugs that we have, maybe we know some drugs are affecting certain pathways more than others. So if we know this sort of mutation has these kinds of effects, then we can maybe make our drug choices a little bit better. But yeah, AML is a very big challenge. Probably, because then we're getting 20 microliters, so it's around 20,000, 10 to 20,000 cells per well. And that's one of the things with the IQ is that you can really sample the whole well. So you can, suck it dry and really get every cell in there. And that's important because, there isn't that many cells per well when people do traditional stem cell type work. So you need to see that whole population. You need to see everything that's in the well. What's left? Are they dead? Are they starting to differentiate? You need all of them. But yeah, the 20 microliters working volume is very tricky. And of course, you need good humidified incubators, active humidity incubators, so that you don't lose during incubation time and stuff. And then we have this hooked onto a robotic system. So we have a system through Biosero to have an arm moving everything around. So from incubator to a shaker to a spinner, onto the echoes, onto the IQ at the end. I think a big chunk of this, as we've been sort of playing around with different softwares, is actually the speed. It doesn't crash my computer. That's like step number one. So we get there faster. So we can set up the gates, and I think in version 8, where you've been able to do the feather light mode, kind of moving down, so that you're not doing the whole thing. So you can set some of your gates up. Obviously, if with an 8-color analysis, there's a lot of gates, and each patient is just that little bit different than the next patient. So there's a lot of gates that have to be moved before you're ready to get the end result in your matrix and your dose response curves and things. So it's very nice to be able to sort of get, you can tone that down, set your things, put it back up, and I get you get a response, and my computer doesn't want to blow up